Hey everybody, this is Larry. This is me doing week 5, the weekly premium challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. And apparently I've done it before, which is actually kind of rare on the premium ones. Oh, that's not true. Just like at least recently enough for me to have it here. But let's take a look. Today we have 426, convert binary search tree to sorted doubly linked list. Convert a binary search tree to a sorted circular link, doubly linked list in place. You can think of the left-right pointers as okay. I mean, that's fine. I think this is a good use of what's it called, the Morris traversal, which I'm not familiar with. I don't know how it works. Well, yeah, I don't know how it works. I just know what it does. But in any case, yeah, yeah. I mean, I think we want to do it in place, which is a little bit tricky. How do we think about this? The idea about these problems is just think about the invariance, right? If you have a tree, you probably, at least if you want to do it in place, I mean, of course, you can just do a traversal and then, like normally you do a traversal, maybe it's over an extra space, that's fine, because then you just kind of do stuff, right? But what we want then is, but yeah, they want the left to be the processor and right to be the successor, right? Okay, fine. But yeah, the idea here is that okay, you're doing this recursively. What is the invariant? Meaning that what doesn't change as you go recursively, right? Here, we want to convert it such that given a root node, what are we doing? Well, we want a root or given a root of a subtree, we want the biggest element that leads to that subtree, right? So basically the biggest on the left side, the smallest on the right side, and that's it. I think that's all you need to know for this problem, and hopefully we'll be able to kind of construct this. Let's say we have some traverse, we have some node, right? And then maybe we want to return two things, which is smallest element, largest element, right? Because those are the two things you need when you return. And yeah, and then here maybe if node is a leaf, right? So if node is a leaf, then we just return node, right? Because it's a leaf, right? And then now we go, okay, left is to go, yeah, I mean, okay. It's a little bit awkward, but it's fine, right? Right, so we have something like this. That means two things noticed here, right, with the invariance. One is that means that you assume the node is already finished on the left side and the node is finished on the right side. Mostly. It's mostly finished on the right side, meaning that, well, actually, maybe I'm lying. What I mean to say is that, okay, node means that all the subtrees are finished except for the smallest node. Because it could connect, it has to connect to the back to or wrap around, right? And or previous node or something. And on the right side, all the nodes are done except for the biggest node, right? Which is in the largest element. And here, if you look at it this way, then the smallest element is going to be left dot, left sub 0 and right sub 1, right? Meaning the smaller element of the left side and the largest element on the right side, right? Okay, so then how does it connect to the current node? Well, yeah, if you root, then you're already not going to be the largest or the smallest. I think I messed up here a little bit. I mean, maybe not quite. It's just that I'm not precise, right? Because the leaves are fine, but you also need the case where we have to check for nodes, right? Because maybe not this one, but even for example, if you look at this one, but there's no 3, then the 2 will go to the right side and this will return none, right? So that will give you an issue. I don't know what to right. Maybe that's fine. Maybe I go like return none. I think if I'm gonna do it this way, then I can just write it here then, right? So if node dot left is not none, then we traverse. Otherwise, left is equal to just node, right? because that's kind of, I think that's reasonable as a sentinel. So no, that right is not none. Then we have this thing, and then now as a result, actually that's not quite true. That's not what I want. Maybe none is better. Actually, well, I don't know. If I'm gonna write it like this, is a little bit awkward. But okay. But my point, and maybe we have to change this. Actually, I have to think it through a little bit. But the idea is that now we have to update this current node, right? And then now, what left is the processor, right? So what does that mean? The processor means the largest element from the left side, right? So then it's gonna be left with one, and then the next element, it's gonna be the smallest element from the right side. So it's gonna be something like this, right? And of course, yeah. So that's why this looks a little bit awkward. I'm trying to figure out the right sentinel. I think this is fine, right? Because then that means that yeah, this will be none, and min will kind of grow up here, right? So I think this is fine now, but definitely still takes, you know, going used to. But then here, then we should be done, right? Maybe. I think this is missing one case where I think this is missing the yeah, maybe smallest largest is equal to this, and then now smallest dot left is equal to largest, and largest dot right is equal to smallest. I think now we're good, hopefully. Give a spin real quick. Oh no, I don't even know what my output is though, so that's a little bit tricky to see. But I think this is generally the idea. Maybe we can remove this for a second. 4, 5, still no bueno. Really, huh? All right, let's print some stuff out there. No dot value, left, right. Okay, so we have 4. Huh. Oh, because the other ones are leaves. So if I came out here. Oh. I see why, but maybe that's a little bit awkward, actually. Yeah, I think this sentinel is a little bit wrong. I mean, the reason being that because it's both the smallest and the largest. No, I think that's fine. But well, I don't know. Yeah, 4. I mean, these are not very helpful necessarily. But let's take a look this way. 4, we have 3 on the left side, 5, so that's right. 2, we have 1 and 3, that's also right. So is it just that I don't set it up correctly? Oh, it's true, I don't set it up correctly. Because even though we set it this way, we have to set the reciprocal one, right? Of course. So that means that left of 1 dot right is equal to node. Yeah. And then here, right sub 0 dot left is equal to node. Okay, I'm just being dumb. Okay, I mean, it's the wrong answer. But that's, oh no, because I returned root, not the smallest. So we have to return the smallest. That's fine, that's an easy fix, right? But yeah, a few minor silly mistakes aside, because we forgot to update the reciprocal links, and then we didn't return the smallest, we returned root. Just I don't know, out of habit, to be honest. I don't think I thought about it until I saw the wrong answers. Let's give a quick submit. None element. Oh, that's because the tree is none. You silly gooses. Okay, fine. I didn't know that that's a possible input, but that's a silly input. I don't know. Like, how is this helpful? Let's. Okay. Hopefully now it's right. Okay, so I am very wrong, it turns out. Huh. I mean, it seems like I'm just missing a base case somewhere. 2, 1, write that 0. Oh, because write 0 can be none. I mean, I kind of, okay. I was just being careless because I kind of add this part in. The reason why I wrote it this way is so that it can be none setting up. But then, of course, that means, I feel like I'm too clever because now it ends up being not too clever anyway, because then we have to do this. And then it just kind of kills the point anyway. Oh, I don't know. None.type has no attribute, right? What? None.type. Left of 1 is none. Oh, whoops. How did that pass? I don't know. Anyway, a lot of silly mistakes aside, that's basically the idea. I think the idea is interesting. This is fine. How much? Huh? Last time I didn't have submissions error, so made a little bit of a regression here. How did I do last time? Yeah, I do an in order traversal. Left, no dot left, no dot right. Oh, huh. All right. Past Larry is a little bit smarter. I think there actually, yeah. This is an interesting problem for sure. I think the way that I did it today, there's merit in learning it this way. But this way is also interesting. I think I mean the is maybe not. I think the only difference is honestly is just that yeah, this makes it in order, and basically we ignore the fact that we need a double linked list, which maybe I should have done, and then after we create a singular linked list from binary search tree, we just kind of put the link backwards or something. So okay, fine. Definitely worth watching that one if you're curious. But yeah, that's all I have for this one. I think. Let me know what you think. Thanks for watching. This is linear time, linear space, right? I mean, we look at each node once. That's it. And yeah, that's it. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.